Unique question here. Some statement is missing actually. Now, by the way, the statement given I will read first and then I will explain which statement is missing. A particle is moving under the influence of a force F equal to K by R theta cap. Now it's not mentioned what is R and what is theta cap. Obviously, in the polar coordinate system, they are, say, this is the rectangular coordinate system xy, and if you have a particle polar coordinate system, the coordinates are r theta. So this is the position vector r and this is angle theta. Theta cap or e theta cap sometimes we call, this is the tangential unit vector. So we call tangential unit vector theta cap, and r is the position vector. So that should have been mentioned here in the problem. By the way, rest all is okay. Dekho. So a particle is moving under the influence of this force along with many other forces. There exists a set of infinite circles, C1, C2, C3, C4 and up to this. If the work done by this force in completing the circular path in each circle is given by W1, W2, W3, W4 and up to W infinity respectively, assume that all circles the particle is moving in anticlockwise sense, determine the work done. See, we will use a certain concept here. See, so force is given as K by R theta cap. So that means this is the position vector R and the force is given by this. So it is force F is equal to K by R. Now it reminds us of, you have to equate in this way, it will make your job easy. If this is the current I, then this is the magnetic field B. So B is, B is inversely proportional to 1 upon R. And then this along this circle, what is the work done? So along the circle, the work done is nothing but integration of F dot dl over this closed loop. Just a minute. So integration F dot dl over this closed loop, and this integration F dot dl will be how much? Actually, see here you can compare. In case of this magnetic field, integration of B dot dl is equal to mu 0 times I. So obviously, there is a current source here, and this the line integral of the magnetic field or magnetic this B field is equal to mu 0 into I. And while one thing you note that if you have a circle here, so what will be B dot dl around this circle? So integration of B dot dl, so around this circle, around marking this by a color code, see, purple color this. So this is equal to 0 because through this loop, what is the current crossing this loop? Current crossing this loop is equal to 0. And it is same for all these circles. See? Suppose if you compare it with line integral of magnetic field and apply this Ampere's law, integral B dot dl is, so integral B dot dl is 0 for this, 0 for this, 0 for this and 0 for everything else. Only there will be this integral around this circle. Now let us calculate, or same way we can find this, that this W2, W3, W4, W5, they will all be 0. They will so this W2, W3, W4, W5 all will be 0. Only one work will exist, that is, only one work will exist, that is this W1. So let us calculate W1. So W1 is integration of line integral of this K by R force times dl. This is constant. So it is actually integration of K by R say around a circle of radius r, we can do this k by r. So integration of dl will be 2 pi r. Integration of dl will be 2 pi r. So therefore this w1 will be equal to 2 pi k, and w2 will be 0, w3 will be 0, all the other work dones will be 0. Here we are finding it by comparing it with Ampere's circuital law. Remember it. It will make your job easy rather than going for a complex mathematical line integral, because it's already a ready-made result for us. So we can, why not use that? So there w1 is equal to 2 pi k. This all will be 0. So 2 pi, that is 3.14 times k, that is 1. So this will be the result, 6.28.